Ah, I see you made it to the Laplace Gateway. Let me show you around. Let's say we wanted to take the integral of e to the x from 0 to infinity. We know that this is just going to be equal to infinity. It just makes sense because you're going to have to integrate this. The answer is going to be e to the x. You're going to go ahead and plug in infinity there. And so you essentially get this thing e to the infinity minus e to the 0, which is just infinity minus 1. This is just going to equal infinity. Well, it really does no good for our integral to equal infinity because a lot of different integrals equal infinity, and we want some kind of uniqueness for this particular function here. So what we can try to do is we can try to multiply this integral. We're going to keep e to the kt. We're going to try to multiply this integral by e to the minus st. Because when we do that, then what happens is we have to basically subtract these two exponents here. So we get something that looks more like this, e to the negative s minus k, and then there's a t on the outside, so just kind of rearrange this a little bit here, dt. Now if we want to try to integrate this function, we're going to get something like this. Remains e to the negative s minus k t up here at the top, but then we're going to have to divide this by the derivative of up here, so it's going to be negative, and then we have s minus k. We're going to set this from going from 0 to infinity. Well, the infinity goes into the t over here, so we're going to get something like negative e to negative infinity divided by whatever, s minus k. It doesn't really matter, those are just constants. And then we're going to have to subtract another negative e. This time we put 0 in there, so negative e to the 0 like that, s minus k. Okay, so this is essentially going to be, well, this goes onto the bottom here, so this turns into 0. And then over here, we just get a positive 1 over s minus k. We have to be careful about the answer to this integral, and we have to put some limitations on the value of s over here. We'll figure out what s is in just a moment. But first, let's put some limitations. We'll notice that if s equals k, then we're going to get 0 back on the bottom here, and so the answer is just going to be equal to infinity, and we don't want that. So let's explore if s was going to be greater than k or less than k. So if it's greater than k, then we can go over here, we could say, well, we're going to get this integral. We get something like 5 minus 1 t, and then we're going to get like e to the negative 4t. And that's great. We have the form of integral e to the negative t, and that's what we're going to get if we have s is greater than k. Okay, so this is what we want. But let's say we got less than k, s is less than k. It's not going to be what we want, because then what happens is we get this integral e to the negative 1 minus 5 t over here, and essentially this is going to be e to the 4t instead of negative 4t. So we get a positive integral, and now all of a sudden it goes back to being equal to infinity. So what we can conclude about this whole s thing is that e to the power of negative st, that's this thing right here, this thing dampens the function. It dampens this function here that we were looking at, and it essentially forces convergence. Because now our integral has converged to this point right here as long as s is greater than k. Let's look a little closer at the value of s. We should be able to represent s as the sigma plus iw. Okay, and the sigma is essentially the damping factor. Okay, damping factor, and this is the real part of the damping factor, but there's also this imaginary part, and later when we look at the Laplace transformations of sines and cosines, we're going to realize that oscillations use s squared, and if you try to square the s's, you're going to also square the i's. So when you square the i's, then it matters, because then you get back to a real number. All right, let's go through some examples of doing Laplace transformations. So we're going to start with the Laplace of 0. And this one's not too crazy because essentially we're just going to pull out the 0. We're trying to take the integral from 0 to infinity of 0 times this e to the negative st. We're just going to pull out the 0, and it really doesn't matter what the integral of e to the negative st is because we're just getting 0 times the Laplace transform of whatever, and so we're just going to get 0 out of that. Not too crazy. Let's try to take the Laplace transform of 1. If we try to take the Laplace transform of 1, then we're essentially just taking the integral of 0 to infinity of e to the negative st, e to the negative st, like that, right? dt. And, well, we're just going to basically get negative e to the negative st. Don't forget to divide this by s. We're going to take that from 0 to infinity, and we essentially get negative e to the negative infinity divided by s minus another negative e to the 0 divided by s. So we clearly are going to be getting 1 over s for this answer. And we have to make sure that the limitation on s is that s is greater than, well, k is equal to 0 in this particular case, as we can see. So let's just make sure that it's greater than 0, and that should work out. So that way, if that was 0, then you'd have infinity, it'd be an issue. Now let's try to take the Laplace transform of e to the kt. And that just means that we're taking the integral 0 to infinity of e to the negative s minus k t. That was the one we did over here, so I'm essentially redoing that one, but make it nice and red over here. 1 over s minus k, and this is where s is greater than k. Let's go for the Laplace transformation of cosine kt. But here's the crazy thing, is that you can plus or minus 2 pi, and you still get the same answer. But anyway, if we do that, the answer is going to be s divided by s squared plus k squared. The limitation on this one's a little different because if s is just greater than 0, we could plug a 0 in for s, and we still get s divided by k squared. I mean, we would get 0 divided by square root of k squared, which is 0, but at least we get 0 instead of getting infinity. So it just has to be greater than 0. And really the key is that, like, when you look at the bottom part here, if you can somehow make this equal to 0, that's where your s's sort of start. Because over here, in order to get this to be equal to 0, s has to be equal to k. So as long as s is greater than k, then everything's okay. Over here, it just has to be greater than 0 because, well, there's no possible way to get rid of this k squared. It's always going to be here, regardless of the value of s squared. Similarly, if we take the Laplace transform of the sine over here, sine kt, and also plus or minus the 2 pi situation, then this will equal k divided by s squared plus k squared, where s is greater than 0. Let's do 2 more Laplace transformations. These are going to be a little bit strange. So we're going to go for the Laplace transformation of t to the power of n. And that one is going to be a really complicated solution. But what we're going to do is we're going to say that it's the gamma function, n plus 1, and then we can divide that by s to the n plus 1. And this is the same as this answer, n factorial divided by s to the n plus 1. For this transform, s must also be greater than 0 because if we put a 0 down here in the denominator, we get back to infinity, so it just has to be greater than 0. For the last inverse transform, we have Laplace of t to the power of n times f of t, some other function. So there's kind of a double function in there. This is going to be equal to, start with a negative 1 to the power of n. And then we're going to take the derivative here, d over ds. This is going to be to the nth degree here. And then we have the Laplace of the original function. And here, we really have to check the original function to figure out what the bounds on s are. So as long as it's greater than whatever it was in that original function, usually it's going to be greater than 0, as you can see, but we just have to check the original function. This operation we've been doing here, forcing these integrals to converge, is called the Laplace transform, and it's just another way to solve differential equations. So let's say we had this y double prime plus a y prime plus a y, we set that equal to e to the x or something. What we can do is we could take the Laplace on both sides, and then we can put this in terms of the Laplace of y. Because you can see we're going to get the Laplace of y right there. Well, if you could figure out what the Laplace of y is, then you can probably figure out what y is. So let's figure out how to do that. Imagine we were taking the Laplace of just ft, just a function here. What that means is we're going from 0 to infinity. We're taking this ft, and we're integrating that with e to the negative st dt. That's what we did over here. And it turns out that this is just basically going to give you f of s. What that means is you integrate it and it gives you some function in terms of s, as we've done over here a bunch of times. All the integrals give you some are in a variable s. Okay, and well, that's interesting because now we can figure out that the Laplace of some function equals essentially the integral of that function in some other variable. This is t, this is s. So what we can do is we can take the inverse Laplace. And so we're going to have the inverse Laplace, L to the negative 1 over here. And we're going to take the inverse Laplace of this function here, f of s. F of s. And when we take the inverse Laplace, that just simply sends us right back to the original function. Makes sense. F of t. So this is the inverse Laplace. And essentially that's the only inverse Laplace function that we need to look at. Is just that. It's a L to the negative 1, fs, gives you ft. That's the opposite of this operation right here. We're not really done yet though, because all we did was take the Laplace of just the regular y. But we also have to deal with the y prime and the y double prime. So let's go ahead and deal with that. The Laplace of f prime of t, and this is going to basically fast forward everything. We're just going to do the integral for you. The answer is going to be s, and then you have the Laplace of ft, and then we're going to subtract f of 0. And what that means is you just get s times the Laplace of the original ft, which is this, and then you have minus f of 0, so you're just going to go to your original function, plug in 0, and usually that's given to you in your question. But we're also going to take the Laplace of f double prime of t, and that's going to be equal to s squared times the Laplace of the original function ft minus s times f of 0 minus f prime of 0. Okay, and this is going to be the Laplace of y double prime, and y. So again, in order to solve the differential equations, all you have to do is apply the Laplace transform across all three, so you get this long equation on the left side. And you're going to set that equal to the Laplace on the right side, which in this case, if k is equal to 1, then on the right side you get 1 over s minus 1. And then you basically solve for the Laplace of y, because the Laplace of y is equal to fs, right? So then, if you know that the Laplace of y is equal to fs, then what that means is you could take the anti-Laplace over here, and that'll take you back into the y, so you can figure out what y is. That's essentially what your goal is when you're trying to solve differential equations. So you have to eventually take the inverse Laplace at the end. Let's take a look at a couple of different identities we should know. We'll start with maybe the Laplace of C1 f of t plus C2 g of t. What we could do is we can apply the Laplace across both functions. So we get something like this. It's going to be equal to C1 times the Laplace of ft plus C2 times the Laplace of gt. You kind of manipulate things in this way. Another important Laplace transform is the horizontal shift. Let's say we have the Laplace of e to the alpha t times f of t. Well, remember that if we are multiplying by e to the alpha t, we're essentially going to be adding in the exponent over here, kind of like what we did over here. It's throw in another e to the alpha over here. Then all of a sudden you get s minus k minus alpha, and at that point we are going to get the fs minus alpha solution over here. This, and that is what that one equals. As long as s is greater than alpha. Try to figure out what this time delay stuff is. Well, let's say I wanted to take the Laplace of some function ft, and I'm going to multiply by the unity of t minus alpha. And what that's representing here is the idea that we're starting this Laplace after t equals 0. So if we have t equals 0, then we're just taking the Laplace of ft. But let's say we want to start it at time 2 seconds. The Laplace starts at 2 seconds. Then over here we have t minus 2 for the unity function. Okay, so let me try to rewrite this in a different way. So we have the integral of 0 to infinity of ft, and then we're multiplying that by the unity of t minus alpha. And then we still have to do this whole e to the minus st thing because we're doing a Laplace transform on dt. Okay, so this is essentially what that means. And all this really means, this is ut minus alpha stuff, is that we are simplifying this whole equation into this integral, alpha to the infinity. Instead of 0 to infinity, it's alpha to the infinity because we're starting at after t equals 0. So now we start at alpha. We're going to go ft e to the negative st dt. This is just a regular old Laplace now. Let's try to compare what would happen if we tried putting in f of t minus alpha here, and then we have the unity of t minus alpha. Okay, so that way we're matching the inputs for the function and the unity here. Here the functions, they didn't really match their inputs here. We have a regular function, and then we have the unity of t minus alpha. So those inputs don't match. But if the inputs do match, then we get these two different answers. So if the inputs match, then the answer to this Laplace is going to be e to the negative alpha s, and then we multiply it by the Laplace of the regular function, ft. And then here, we're going to have to look at the original function to figure out what the limitations on s are. Usually it's going to be 0. So again, if the inputs match, then we just take the e to the alpha s and the Laplace of the original function. But if the inputs don't match over here, then what we're going to do is take e to the negative alpha s, and we take the Laplace of f times t plus alpha. And again, we have to look at the original function to figure out what the limitations on s are. But why this reasoning here is because look what we did. Didn't we just take t minus alpha and add alpha? So all we did was just add alpha. Alright, let's really try to figure out what this unity function means. We have u of t minus alpha, and this simply represents that we're going to have the function is going to be either 0 or 1. Well, this is either 0 or 1. It's 0 when t is less than alpha, and it is 1 when t is greater than or equal to alpha. this is the piecewise notation for the unity function. Let's try to remember what the piecewise notation means. So we have two functions, f1 and f2, and we want them to start. See, f1, we're going to start it at alpha initial, and then this is going to go all the way towards alpha final. And well, same thing over here. I guess we'll call it beta initial, and then some beta final, whatever. So what we can do is rewrite this, and we essentially say that f of t is equal to f1, and then we have to do some subtractions for these functions. So we're going to do unity of t minus alpha initial, and then we have to subtract the unity of t minus alpha final. And then we could add the next one, f2. We do the same operation here. So unity of t minus beta initial. And then we have to subtract the unity of t minus beta final. And now we can figure out what the piecewise is, f1, f2 at these specific points. It's a little bit tedious there, but that's how we can do that. And one final little quick Laplace. We're going to take the Laplace of the unity function itself. So u t minus alpha. And if we were to do that, the f of t is just 1 here, isn't it? So we basically get that e to the negative alpha s, and we're just taking the Laplace of 1. Okay, and so then just going to be s is greater than 0 for the limitations. And there we go. Hopefully this was helpful. Thank you for visiting the Laplace Gateway.